So good morning, everyone. Welcome to the BRO seminar series. It's my pleasure to introduce our today's speaker, Dr. John Mclennan, talking about using flowback and temperature for closure stress diagnosis. Let me give you a brief introduction about John before we start. Dr. Mclennan is a professor in the Department of Chemical Engineering at the University of Utah. He has been a senior research scientist at the Energy and Geoscience Institute and adjunct professor in the Department of Civil Engineering at the University of Utah since January 2008. He has a PhD in civil engineering from the University of Toronto, awarded in 1980. Before joining the university, he has more than 35 years of experience with petroleum service and technology companies. He worked 9 years for Dow Schellenberger in their Denver, Tulsa, and Houston facilities. Later, John was with TerraTech in Salt Lake City, Advantech International in Houston, and ASRC Energy Services in Anchorage. He has worked on projects concerned with subsurface energy recovery, including hydrocarbon and geothermal, in a variety of reservoir environments throughout the world. I also would like to acknowledge Dr. Peng Jujing, who is a postdoctoral researcher in the Energy and Geoscience Institute at the University of Utah. His work is on the stimulation simulation, in situ stress interpretation, and wellbore stability for the Forge project. So with that, John, welcome to our seminar series, and let me hand it over to you to start your talk.
Thank you, Sahar. And as everyone can see from their screen, I've simplified the title a little bit from what you might have seen. And this simplified title contains two elements. The first element is stress determination, which is relevant to any subsurface engineering activity. And that activity here is going to be some well bores. And the second element is something called Forge. And what is Forge? Forge is a Department of Energy project, and this acronym stands for Frontier Observatory for Research in Geothermal Energy. And we owe a lot of gratitude to the Department of Energy, particularly the Geothermal Technologies Office, and many, many stakeholders throughout the country, and particularly in Utah itself, where this operation is. So what is this all about? Well, let's consider geothermal. Let's consider conventional geothermal that we're all somewhat familiar with. What does a conventional geothermal operation have? It has three subsurface elements. It has temperature at a shallow enough depth that you can reach it with economically with drilling. It has conductive natural fractures that are able to conduct fluid. And in fact, the third element is that fluid itself that is moving through these natural fractures. Well, having these three elements restricts viable conventional geothermal operations to restricted geographical areas, as would be well familiar to people at the BEG, plate boundaries and other situations where there is heat flux or heat close to the surface. Well, suppose that we have a situation where we don't have all three of those elements. Suppose we have a situation where we have heat in the ground, in the earth, that is moderately close to the surface, but we don't necessarily have this conductive fracture system, and we don't necessarily have this moving fluid. Well, can we exploit this and add those two other elements, the conductive fractures and the fluid? And yes, indeed, that is the principle of an enhanced geothermal system, where you drill multiple wells, you interconnect those wells with hydraulic fractures, and you circulate a working fluid, water at least in the early stages, through that system so that you can extract energy. And this was the vision of the Department of Energy. Well, it's been the vision since the 1970s, but this vision was reestablished about 5 years ago when the DOE set out awards for 5 desktop studies for field locations in the United States. There were a couple in California, one in Oregon, one in Nevada, one in Idaho, and one in Utah. That may be 6, but there were only 5. And from those, using government speak, it was down selected to 2 sites. One that Sandia National Laboratories operated in Fallon, Nevada, and one that the University of Utah operated in Milford, Utah. And each one of those sites was awarded $10 million to do drilling and exploration and make a case for being the site for a field laboratory for research in enhanced geothermal systems. And ultimately, in 2019, we received that award for our site in Milford, Utah. And it sort of met the criteria. It was seismically benign, relatively at least. No potable water in the area, so there's no competition for other uses. A conductive heat transfer mechanisms in the reservoir that we're dealing with, and temperature at depths between 1.5 and 4 kilometers that sort of met the criteria, somewhere between 175 and 225 C plus or minus. So with this award, basically, we have a scenario at Forge that's shown in the accompanying illustrations. We have in the middle an elevation view of what the subsurface laboratory is going to be, and at the right-hand side, a plan view. So the initial plan is to drill the blue well, which we'll call the active well or the injection well. We'll drill the blue well, and actually we're going to spud that well in about 2 weeks. And that well is going to be drilled to just under 11,000 feet total length, measured depth, and it'll be at a depth of about 8,500 feet below the surface, true vertical depth, and the bottom hole temperature will be about 250 degrees C. We'll drill that well, and then sometime shortly thereafter, we'll do 3 small fractures at the toe of that well, and those fractures will then be monitored microseismically, and we'll drill into the seismic cloud with a second well shown in red here. And so that's the premise at Forge. In a commercial operation, and at Forge we'll leave most of the well open, and that well is left open so that the DOE can issue solicitations for research that's related to advancing this geothermal technology. And this is what would happen at a Forge scenario. In a commercial scenario, what you would do is you would inject cold, you would not just fracture the toe of this well, you'd fracture all along the length of the well, as we're familiar with from oil and gas operations. And in this, it's somewhat different than oil and gas. We want to have frac hits in this case. We want fractures that intersect both wells, that connect these 2 wells, so that you can inject cold water down one well. That cold water passes through the system of fractures, picks up heat, and is produced out of the second well. It's taken to the surface, flashed to steam, or run through an organic Rankine cycle plant. So that's the premise. And this is a very abbreviated geologic overview. At the eastern edge to the right, we're seeing the mineral mountains. There's an operating power plant that is shown here, a geothermal plant called the Blundell plant. And then our site is maybe a couple of kilometers to the west of that. Now, the interesting thing is that there's a hydrologic barrier or some sort of this opal mound fault divides these 2 geologic domains. The domain to the east has convective natural fractures carrying hot fluid up from depth, hence the power plant. To the west of the opal mound fault, and the opal mound fault is poorly described, but to the west of it regardless, it is a conductive regime where heat moves through the formation largely via conductive heat transfer. The elevation view to the bottom shows a situation where, and it belies the complexity, obviously, that the mountains, a block of the mountains to the east has actually rotated at some time in the recent geologic past, and a contact has been developed between the granitoid body and superposed alluvium that has been shed from the mountains. And this contact dips at about 30 degrees to the west. And the well that we're going to talk about today, where a lot of these measurements were done, because stress is relevant to everything that we do subsurface, and so we're going to concentrate on stresses, is well 5832, and it was drilled to about 7,500 feet. And as you can see from this illustration, it penetrated about 4,500 feet of granite. So what do we have? Well, this is looking to the east. This is looking to the mineral mountains that I referred to. And you can see in the foreground, you can see that there is a lot of basin fill, alluvial basin fill derived from these mountains. And we have three wells that are going to be of interest today, at least in the initial part for the stresses. The first is a shallow monitoring well drilled into the alluvium, just under 1,000 feet deep, and it contained a geophone and an accelerometer. That's well 6832. The second well, about 1,000 feet to the east of that well, is well 7832. And this well touched granite at about 2,600 feet, and it TD'd at about 3,300 feet, 3,280 feet. Historically, at the past, periodically, we've run geophones in this well, 100-foot spacing, 12 geophones, and they straddling the granite contact. And this well also has a permanent DAS cable, distributed acoustic sensors, cemented into the backside. Now, so we have those two monitoring wells, and then we have this well that I mentioned earlier, well 5832, a near vertical well drilled to about 5,832 feet that has been used to do a lot of, we cored this well, comprehensive logging suite, and two stress measurement campaigns that I'm just going to describe briefly before I go on to future plans at this location. So what have we got? We have this well 7830 or 5832, excuse me. And one aspect of this well is that, well, it's 7,500 feet deep, but the bottom 150 feet or so are open hole. And so in that open hole region, we've carried out two stress measurement programs trying to look for the stress field in these wells, looking to see in a more recent campaign how much seismicity, microseismicity we generated, understanding whether we get shear fractures or tensile fractures, and looking at various measurements techniques such as flowback for determining in situ stresses. And so in that open hole section, as I said, two stress measurement campaigns have been carried out. We're going to call that open hole section zone 1. And the first campaign was carried out in 2017. And it doesn't really matter, but there were 8 injection cycles that were done in this well. And so you can see that this is a bottom hole pressure measurement versus time. And the reason it starts at 0 is that we're following the pressure temperature tool as it's lowered into the hole. So initially at 0, down here it gets to the bottom of the hole and it's reading about 3,200 PSI, nominally the in situ pressure, certainly the hydrostatic pressure in the wellbore. And then a number of injection cycles and shut-in cycles carried out. And the rationale for these injection and shut-in cycles is that you can diagnose the pressure signatures and make inferences about the in situ stresses. And so a number of measurements were made varying from small volume injections where we just pump at a low rate, we just break the rock and shut in the valves at the surface and monitor the pressure decay, to situations in cycle 5 here where we did what the industry characteristically calls a diagnostic fracture injection test. Same principle, just bigger volume, slightly bigger volumes of fluid, slightly higher rates, and once again, you process the pressure time data after this well, after you've stopped pumping, and from that, you look for characteristic signatures and infer when the fracture closes. Inference of when the fracture closes, you attach to some sort of in situ stress. If we assume a true Andersonian stress regime in an extensional environment, we're presuming that this is the minimum horizontal stress. And so multiple cycles carried out in this particular zone. And this is just one example. What you're showing here is you're showing pressure on the y-axis and time on the x-axis. And we're showing tubing pressure, the pressure in the annulus, so the pressure above a packer that was at the bottom of the well and between the injection string and the casing. So this is an area that's only pressured benignly. And then the tubing pressure, because you're pumping down the tubing, and you watch and you monitor the pressure decay. So we pumped in, we've broken this down, created and propagated the fracture, allowed shut the well in, closed all the valves, monitored the pressure, and looked at the pressure decay and processed that information. Concurrently, we had, excuse me, microseismic measurements from the geothermal wells. Now, the issue with these wells is that these tests were designed to see if we could locate the signals. Excuse me, if we could detect the signals. Location is a little more problematic because the well that the measurements were done is what? It goes, as I said, to about 3,200 feet in depth, but it's only about 1,000 feet away from this well. So basically, you have a situation where you're looking down on this, and the resolution from Schlumberger's perspective is not adequate for them to put locations on these. And so we're satisfied for the time being that we can just create events, and even that in itself is useful. Future activities, additional monitoring wells are being drilled so that triangulation is going to be possible and location is possible. One of the very interesting things about this open hole campaign, and this is from 2017, is we have FMI data from before and after the fracture treatment in that open hole section of well 5832. At the left are a static and dynamic FMI. So basically the same image, but the dynamic image puts the extrema on the colors within a 10-foot moving window and sort of exaggerates the coloration. And so it's the same vision, the two on the left, and the two on the right were taken after the fracture. So you can notice some interesting things. Basically, you can notice some prescient tensile features along the well beforehand. And afterwards, after this fracture, you can see that those were exaggerated and increased, that they were vertical longitudinal fractures separated by 180 degrees, a classic example of tensile fracturing occurring along this well. Now, one of the potential reasons for this, and the potential reason that you're having these fractures exist beforehand, is not that they were specifically drilling induced, although they were characterized as drilling induced fractures by the logging company. They're likely thermally induced because you have cooled, chilled drilling fluid. To be able to drill this well, you're chilling your drilling fluid. You have chillers at the surface, and you're chilling the drilling fluid, and the expansion of the well because of the cool down and the thermoelastic stresses that are actually becoming more tensile have led to vertical fractures. And so one extremely interesting feature. The purpose of this well was, one, to see whether we could actually frack it, and indeed we could. And the fractures actually initially started at very low closure stresses, probably associated with these thermal fractures. With time and with larger volumes of fluid, as we grew the fracture away from the wellbore, the stresses became more compressive, and we'll see that in a couple of minutes. So that was one part of the well that we worked with. Then, and that was in 2017, and we repeated it in 2019. And in 2019, we also said, well, we're going to move up the hole to a cased and cemented section of the well, and we're going to see if we can break down some perforations and create a fracture. And there are a lot of challenges and a lot of issues that we were looking at. First of all, we identified a zone that preferentially had, from the FMI and stress analysis, what we visualized as critically stressed fractures. That as we injected, and progressively as we injected, we're moving in increasing pressure above the static hydrostatic pressure from left to right here. I think you're going to see some red ones appear somewhere in here. Yes, somewhere in here. It's a typical analysis, a little deeper than this zone, but just demonstrating what's going on. Is that the analysis is demonstrating that there's an occurrence over the 10-foot isolated zone in this perforated interval, that we're going to have a fair number of critically stressed fractures, and we'll have a pretty good chance of breaking this well down. You know, you always like to shoot for success on your first try. So we picked a zone that we thought had favorable number of favorably oriented natural fractures that we could possibly shear and or dilate in addition to any sort of tensile fracturing that we're having. And so we were looking at propagating these critically stressed fractures, assessing it whether or not shear occurred, and I'm not sure I know the answer to that yet, and establishing baselines and looking for any sort of degrees of anisotropy, because we are fracturing in this zone, and then we went to another zone without fractures. And was there a difference between those zones? And indeed there was, and I'll get to that in a minute. So we have this first perforated, cased, cemented zone that we were going to fracture. We did fracture to test for initiation, for breakdown, and reopening pressures. Strangely enough, this is maybe one of the first geothermal wells where anybody has treated a well through perforations and cement. Most geothermal wells to date have been relying on convective fractures and leaving contact with those fractures open hole in the wellbore. Now we want to be able to control the growth of hydraulic fractures from this particular well. So we need to be able to isolate between individual fractures. So that was the decision that we would need to be able to test in future wells whether we could break down from a cemented casing situation. And we picked those zones. How do you pick those zones? Where are you going to locate these? Well, we had 3 criteria. First of all, we didn't want any casing collars. We didn't want any joints and connections where the casing was occurring, because that is going to impede the perforating, for example, and it's going to affect our injection possibly. The second thing is we wanted a good bond with the formation. And in these wells, it's always difficult to tell cement bond, but probably a decent cement bond showing up from the VDL here. And the third thing is the processing of the FMI data and looking for a preponderance of favorably oriented natural fractures. So we found those fractures, we selected this zone, we perforated it, we isolated it with a packer and a bridge plug, and we pumped into this isolated zone. And once again, we did a number of injection tests, some low rate injection tests, some higher rate. This DFIT, for example, would be at 5 barrels per minute for about 10 minutes. This cycle 9, as I recall, was closer to 15 barrels a minute, getting up to commercial frac rates, well, still lower than what you would conventionally use in the shale, but it's a single cluster. And so the rates might be a little, might be reasonable, but multiple injections, long shut-ins. I mean, you can see these shut-ins were a matter of tens of hours. And those longer shut-ins allow the pressure to bleed off into the formation and the fracture to gently close on its own and infer the in situ stress and the permeability from these fractures. Now, here is one that is the first time we actually broke this formation down. This was on the 4th injection cycle. The first 3 cycles we were pumping at low rates and we may not have broken the formation down. But this is a textbook example of a hydraulic fracture. And everyone can see that, right? We've got pressure. In this case, it's surface pressure versus time. And we're showing a rate. And so this rate leveled out at about 5 barrels per minute. And this is pressure. And we see 2 indications of pressure. We see a pressure that existed when we were pumping down the tubulars. That's we were pumping down those. And the pressure that existed in the annulus. Well, I thought I said that the annulus was isolated from the rest of the hole because there was a packer. Well, unfortunately, the packer failed. So when the packer fails, you get pressure that's recorded in the annulus all the way up to the surface. Well, this is actually a benefit in some ways, other than you're putting pressure on the casing. The benefit is this is what is called a dead string. And what it means is that you have a measurement of pressure, but you do not have any friction in that pipe because there's no fluid flowing in the annulus. So if I take that annulus pressure and I add the hydrostatic pressure, that's directly the bottom hole pressure without tubing friction. Nevertheless, you have 2 measurements of what happens at the surface. So you're pumping and you're pumping and you're pumping. And finally, all of a sudden, this formation lets loose. Okay, it breaks. A fracture is initiated, and initiation and breakdown are almost coincident. Initiation is the start of the fracture. Breakdown is a pseudo-uncontrolled, temporarily unstable propagation of a fracture. And with that happening, you create a fracture and a volume is created. So fluid gushes in, the pressure goes down, but ultimately the fluid catches back up. You start to rebuild pressure and you propagate in some fashion like this. Then you stop pumping and immediately stop pumping. There's a drop in pressure that's associated with friction in the fracture. In this case, friction in the tubulars as well. And then there's a pressure decay that follows. And at this particular zone, we did measure significant microseismicity. As I said, all we can infer is we got events. We cannot explicitly locate them better than what is saying. And so this upwards migration to the west is an artifact of the interpretation. And we were just glad to be able to see that we could record them so that in the future, or we could detect, so that in the future we can also locate. We would have liked to locate, but it just wasn't in the cards. So that was the second zone that is done. We'll call that zone 2. And significant, fantastic, interesting data from that zone. Zone 3 was the zone that we'll call them non-critically stressed fractures, or I sometimes call them anti-critically stressed fractures. And indeed these were. And we picked this zone once again on decent cement bond. It's probably not quite as good as what we had in the previous case, but this was a foam cement that was behind here, so it's sometimes difficult to tell. A processing of a 10-foot sliding window of the FMI data to identify presence or lack of critically stressed fractures. In this case, we were looking for a lack. We wanted to compare. And then finally, trying to avoid casing collars. And in this case, we did a good job of picking a zone that was going to be difficult to break down. Indeed, because what we found in this particular zone is a couple of things happened. We took the pressure up to the limits, less than the limit of the packer, and the packer failed, developed a leak. And so that means that you're pumping down the tubing, and the tubing is immediately exposed to the backside of the well. The annular space between the tubing and the casing. It's also exposed to the wellhead. And the surface rating of the wellhead was 6,500 PSI. That was all we were able to take the pressure to. So 6,500 PSI, we had to walk at that level. And these, so you can see right in here, this is a test, surface test. So the well wasn't exposed, but sort of holding out at 6,500 PSI here. At this pressure, the packer failed. And we said, okay, well, we'll keep going, but we can't go above 6,500 PSI. So it's common in these tests. We sort of dance around that area. You try injecting, shutting in, injecting, shutting in, repeating this cycle of injection and shut in until something good happens. Well, nothing good happened in this case because the bridge plug, which is the bottom packer, failed at 6,500 PSI. And what that means is that while we were pumping into this zone, we recorded microseismicity from the open hole zone right at the bottom of the hole here and the zone that we had previously fracked here, because there were perforations here that were open, and now all of the fluid was just gushing down. So at this point, we were out of budget, and so we packed up, and we had done a set of measurements in 2017, a set of measurements in 2019 in 3 different zones, a barefoot open hole section right at the bottom of the well, as can be seen here, a zone at about 6,964 feet, and this treated extremely well. And this zone that, hey, if we had a little more pressure, if our wellhead capabilities had been higher, and if we had, we could have broken this zone, we believe, but we just didn't under the circumstances. So to put this all together, we spent a lot of time analyzing the data and using multiple different techniques within the industry for analyzing the data. And as you can imagine, if you use different techniques, you get somewhat different answers. And so what this plot is showing is it's a compendium of the stress gradients that were measured. So the stress gradient we're taking to be the minimum horizontal stress, and we're arguing a vertical and horizontal stress field. And that's probably not quite the case, as you know, we talked about inclined contact. So it's probably not the case, but it's probably close based on all indications we have, including the natural fractures. And multiple different measurements. Each one of these indicates a cycle of injection, and the A and B or C indicates a different interpretation test. Measurements done in the open hole section in 2017, not too different in 2019 when we repeated those measurements in the same zone. And in the perforated zone, one of the things we see is that there's a couple of interesting things that we see that are of scientific interest and of relevance to geologic and engineering understanding. So what we saw is we saw that the cased and perforated hole always gave inferred stress values, closure stress values that were larger than in this open hole zone. And so you could argue that, well, there's a tortuous path near the wellbore, and that might explain why injection pressures were higher. It may or may not explain why shut-in pressures were higher. And it does indeed explain shut-in pressures are higher if those tortuous paths were from a fracture system, and you're likely opening a pre-existing fracture system, at least initially, or you're soon connecting to an existing fracture system. And that fracture system was not directly perpendicular to the minimum principal stress. And so we're going to argue that in the open hole with the thermally induced vertical fractures, we're seeing a vertical stress measurement, or seeing a horizontal stress measurement. In this case, maybe you were initially opening a fracture system that was inclined to that. The other thing that's particularly interesting, and I don't necessarily show it with the data here, but you can see it, is that, and we'll go back, maybe, we'll go back, and what you can see is that the more you pump into this formation, the higher this pressure becomes. And we say, aha, this doesn't surprise me. This is poroelasticity. I've seen this oftentimes where the formation pressure increases. As a matter of fact, there's a number of historic cases for example, in coals in the Piceance Basin in the 80s and 90s, where people did so much pre-frac injection testing that the pressures increased because of poroelastic effects to a level where they could not carry out the fracture because the tubing pressure was too high for the fracture. So it potentially is some sort of poro or thermal elastic effect, or some sort of stiffening from the fluid that's going in here. But I caution everybody to sort of view this somewhat differently than our conventional vision of poroelasticity. When poroelasticity was initially developed in the oil and gas industry, it was the sweet spot for that back in the 80s were 20 millidarcy formations, where indeed you could see local changes in pore pressure and consequent changes in the total stress. Now we're talking about a very low permeability matrix and natural fractures that are providing the equivalent porosity for the development of increased pressure. And so I think that there's a lot of room for research in this particular area in terms of understanding these effects, because you're having effectively what I call self-shadowing. It's shadowing of an individual fracture from inflation of proximal natural fractures that have been filled with fluid and back stresses that are associated with that. And we don't completely understand the consequences of that in terms of shadowing in this type of formation when there are multiple parallel fractures that are injected. So a pretty important problem. In the interest of time, I'm going to skip through very, very briefly some of the other interesting elements that we found in here. Conventionally, when we do these measurements, we'll pump into a well and we'll shut it in. Well, when you have a very low permeability formation, that shut-in can take a very, very long period of time. So what happens if we help the shut-in along? What happens if rather than allowing fluid to just flow into the formation, allowing the fracture to close because of leak off, that we actually flow the fracture back, that we open a valve and incrementally allow fluid to come back to the surface. And this is not new. It's been talked about since the 1990s by Plon and Nolte. Folks at Shell, Savitsky and Dudley have been doing it. And we don't have enough time to really go into the theory behind this, but basically what you're doing is that you're rather than just shutting it in, is that periodically you're opening a choke at the surface for a very, very short period of time. You're allowing fluid to flow back. So you're removing the fluid that's holding that fracture open artificially by bringing it back to the surface. And you're closing that choke, you're opening that choke, you're closing that choke, and you're bringing it back incrementally. And what happens is that progressively, as the fracture is closed because of this incremental opening and closing of the choke, these mini flowbacks, is that with time, basically this fracture system stiffens up. And by stiffens, it means that the rate of change of pressure with the volume that is flowed back becomes higher. And eventually, the stiffness of the situation reaches what it was before you started. And what it was before you started is to look at this. This is surface pressure. This is the injection pressure. This is the whole injection job. And the slope of this line, the differential of pressure with respect to volume, is the stiffness of the system. And this is before anything had occurred. So once the system returns to a stiffness that's correlative with the stiffness beforehand, then you can infer that the fracture is closed. And this worked out kind of interesting. It gave us lower numbers. We received some criticism, and it's probably valid that we may not have started flowing back soon enough. But regardless, we're very, very upbeat. And actually, there have even been some recent JPT articles by others about using flowback as something where you can do a defect measurement in a matter of an hour, maybe a little more, rather than having to wait days or at least many, many hours. And so it's really an interesting test. The other element of interest in all of this is using temperature as a diagnostic. And here's an example, okay? Here's one of these tests. We're injecting, and here's the bottom hole pressure shown in blue. And you shut in, and you see a blah sort of trend, right? It's just a nice pseudo-exponential trend. But look at what the temperature does. It's initially heating up because we're bringing fluid into the system from higher up in the tubing. And actually that fluid turns out to be a little bit hotter in this particular case. And once we stop pumping, the temperature starts to decay, and religiously we see a turnaround. And we're attributing this turnaround as a conversion from convective heat flow into the fracture system to conductive heat flow as a mechanism. And we actually have something like a Nusselt number that we're using to come up with an indication of this. And this processing of temperature data confirms very, very well with conventional interpretation of pressure data for picking closure. And it's much easier to observe in many cases. And certainly it's easier to observe in its raw form. But in the interest of time, I'm just going to skip through that. And you're all sitting here and say, well, why do we care? Well, we care because all of the stresses, all of this engineering works in creating these fractures in this new well are governed by creating hydraulic fractures. So we need to be able to drill the well in the correct direction, and we need to be able to use the in situ stresses to design these fractures and infer how much fluid we pump in so that we can have an adequate degree of microseismicity from 3 small fractures that we'll do at the toe of the well, and allow us to drill into that microseismic cloud and create a connected wellbore system. That will leave the Department of Energy with all of this real estate here for the solicitations for people to try out various EGS technologies that are appropriate. So where are we at now? So quickly, and this is all very quick, I understand. Let's look at what we're doing now. Well, 7832, 3,200 feet deep. Periodically, we'll run geophones in that well. It has a DAS cable. Shallow well, less than 1,000 feet deep with accelerometer and a geophone. This deep well, we'll run geophones in it periodically. That was the well that's been the subject of discussion to date. And somewhere out here, and we're looking west in this particular view, we're going to spud in 2 weeks and drill a well at an inclination of 65 degrees at 105 degrees from north, which from geologic inferences and from FMI data, we're inferring to be normal to the direction of the maximum principal stress. This is the rig that is going to be mobilizing. It'll be moving out in the next week or so, looking down the catwalk and the pipe handling equipment. And this is a cross section of the well that it's a complicated well design that has well, not complicated by oil and gas standards, but by some standards it's complicated because it has a liner hanger so that we can guarantee cementing effectively here and then cementing a tieback above. But this is distorted. The actual angle is going to be about 65 degrees to the horizontal. And this total depth will be just under 11,000 feet. This measured depth, or excuse me, this true vertical depth is going to be 8,500 feet below the surface vertically, and the bottom hole temperature will be about 250 degrees centigrade. And so, yeah, it all sounds pretty good, but we're all looking for success, but we sort of wake up in the middle of the night in the cold sweat and think that people have been trying to do this for 50 years, and are we going to be any different? They've been doing it since people tried to do this at the Jemez Caldera in New Mexico in the middle 70s, right through some recent ones in Korea that were shut down because of seismicity. Cooper Basin in Australia, a lot of money spent, 1 megawatt about commercial power. So these things haven't been working easily. We think we have a better chance by using directionally drilled technology and adapting oil field technology to frack between the wells, but that's yet to be determined, but we remain positive. Still technical challenges. Big technical challenges are packer failure. This is a failure of an inflatable open hole packer and releasing enough energy to do this amount of damage to tubing. So, and temperature and differential pressure for these devices is a real challenge. And we do have solicitations actually on the table from the DOE to look at tools now that can isolate devices. And you might recall that I mentioned packers and bridge plugs failing. In the last campaign, we 4 out of the 5 packers and bridge plugs that we used failed below manufacturers' recommendations. Second thing we worry about is cementing and casing failure. It's become a big issue in the oil patch. We'll watch out for it now. It becomes even more important in geothermal because you can have trapped water reaching high temperatures and causing problems. The third thing that we're obviously worried about is what sort of fractures do we frankly create in this system, and are they this ideal? Is there significant stress shadowing? What sort of clustering should we be using? Are sliding sleeves more appropriate than a clustered plug and perf configuration? We won't know that in this well, but in future wells, we'll be evaluating different completion technologies. And so, can we create those fractures? What sort of rates should we be pumping at? Some people argue that we should be pumping at low rates so that we're hydraulically shearing and self-propping via shearing. Other people are vehemently opposed to that and are arguing pumping at higher rates so that you have an extensional failure at least a dilation of shearing fractures and an interconnection of a natural fracture system that ultimately grows in a nominal direction that's perpendicular to the minimum principal stress. Can we propagate these fractures from an injector to a producer? What happens when we drill that production well? Well, we're sure hoping that we're going to intersect the fractures. We're sure hoping that the microseismic cloud is an approximate indicator of where those fractures are going. And we'll see if we have to take on additional efforts and fracture the production well to cause injection. And then finally, and you people from all the work that you've done with water disposal in Texas are more familiar with this than I, is earthquakes are a real consideration. The Basel geothermal program in 2009 was shut down because of seismicity. You know, the people in Basel are very, very sensitive to this because in 1356 there was an earthquake that leveled the city. I forget the magnitude. I think it was a 6-ish magnitude, and then certainly this being the case at Basel. So we're watching with this carefully. significant monitoring, traffic light systems, and hopefully a more benign seismic area than at Basel. And then the final thing that we'll talk about before concluding here is, how does this all work? Suppose everything goes really well and you can get multiple parallel hydraulic fractures. Are those hydraulic fractures going to be independent? Or is there going to be crosstalk? Are those fractures going to be flowing from one fracture system to another? In fact, if I look at it in this schematic, is what I want to do is I have a injection well and a production well, and I want to simplistically have multiple fractures interconnected, but I want to have uniform flow between the wells in each one of these fractures. And that's going to require technology development for flow control at higher temperatures, isolation technologies, and a significant effort. And I think we'll see that some of that effort, hopefully at the FORGE program through solicitations in being able to control those. So in summary, I didn't talk as much about the flowback and temperature measurements of in situ stress. Concentrated more on stress in general, the measurements of stress that we've got, and what's going to go on in the future here. And I think the word is just stay tuned, and because we will be starting to drill in about 2 weeks, 2 to 3 weeks. So I'd be happy to try and answer any questions. I think my time has elapsed, but pleased to take any questions.
Thank you, John, for your interesting talk. So there are multiple questions in the chat. I will read the question for you. The first one is from Mohsen. Are there any propans planned to be injected during the frac operations?
Not initially. We're going to, first of all, we're going to try and keep this initially simple, and proppant will be ultimately something that we will evaluate. Now, the thing that one has to recognize in this particular case is placement of proppant in these wells is probably a little bit different than what we would do in an oil and gas well. So think about how you place proppant and what your proppant schedule is in an oil and gas well. Okay, we go in and we frack and we pump our pad, and then we start at half a pound per gallon, and we gradually increase our proppant concentration so that just before flush, we have the highest proppant concentration, so that we have the most proppant that's placed at the mouth of the fracture. Well, that's probably not appropriate in these particular wells. And the reason being is that the mouth of the fractures is going to be at the injection well where you're injecting cold fluid. And what's going to happen with the cold fluid is you're going to have fracture aperture increasing on its own because of thermoelasticity. And so you'll have cold fluid entering, and you don't need as much proppant there, or we're speculating you don't. But where it intersects the injection, the production well, you're going to have a hot fluid going in there, and you won't have the thermoelastic assist to keep that fracture open. So ideally, you may want to have proppant or increased conductivity at the far end of this well rather than at the near end. And the other considerations with proppant are, first of all, you cannot use silica because with the temperatures that proppant will ultimately dissolve. We've done experiments where it looked like bauxite may work. Some other people have done experiments where they've said that they thought silica might work, but I can't see that. I just see from a geochemical point of view that you reach a temperature regime, maybe 250C, where it's gradually going to see the dissolution of the proppant and the degradation with time. And ultimately, what we've also seen in the laboratory is we've seen significant creep at temperature that has even superseded some of the impact of the proppant.
Okay, there are other questions, but due to the time constraint, we have to quickly go over them. So one is from Leo Sierra. It's about phase 2C zone 2. Have you been able to see the water hammer effect in the annular or casing pressure? If not, why is there a water hammer in the casing pressure?
This is a good question. And if I can go back, first of all, it's a good question because it is relevant information. The second thing I have to say is mea culpa. We have not analyzed the water hammer as much as we should. Let's just see, do I see that figure? Because there certainly is relevant information in that water hammer, and I'm suggesting this individual is probably more familiar with this than I am, but that information is really valuable, and you can see it a little bit here, is that when we shut down, and it was a hard shut in at the surface, and we did see a water hammer. And so what we want to do with water hammer, and well, this is just my perspective for the industry, and maybe this person is working on R&D on it and knows more, but we want to look at two things. First of all, we want to look at the water hammer in terms of the immediate connectivity to the well, between the wellbore and the formation, the potential for ultimately diagnosing, and secondly, the potential for ultimately diagnosing dimensions of fractures. There was a lot of work done in the 90s, particularly by Paul Vandenhoek at Shell at that time, where we looked at water hammer effects at the surface and tried to infer a fracture length from those. But that is a fantastic question, and it's something that we at Forge have not paid enough attention to, and I think that there's a really valuable set of data that we can discriminate from that information.
There's one question from Alex Son. Thanks for the nice talk. Have you tried to infer fracture distribution based on distributed temperature data?
We do not have DTS in this particular well. This particular well was drilled under a budget that where we did not use DTS. I think future efforts include much more extensive use of fiber. We do have a DAS in one of the offset wells, and temperature, but that well was a monitoring well and it wasn't fractured. But this is another good point. In the upcoming well that we're drilling, this inclined well, just because of the uncertainties in drilling this well, and it's one of the first highly inclined wells in such a granitic formation, drilling at maybe 10 feet an hour, we declined to run fiber in the backside. Concerns about rotating guns and things like this. That being said, the petroleum industry is doing it all the time, and actually there's a company called Fervo, a geothermal company, that has recently had great success with orienting their guns, and so we'll revisit that in the future, and we'll certainly run fiber in future wells.
Next question is from Peter Aikable. How do the near wellbore thermal effects as opposed to the poroelastic effects affect the stress measurements?
Well, trust Peter to ask a question that I can't answer, but I think that this is an element for real research, and it's something that I think is particularly challenging. Actually, let me go back to this. This phenomena is near wellbore for sure. This breakdown. We are growing this fracture away from the wellbore. We repeated this exact same simulation immediately after a 24-hour shutdown. I'm not showing everything there. And we saw a perfect curve. Okay, we didn't see the breakdown because the tensile strength is gone. It just rolled over nicely, but it treated higher. And the question that people keep on asking is, why is it treating higher? Is this a thermal effect? Is this a poroelastic effect? And then secondly, to more specifically address this question, is that in the measurements that we have done, can we discriminate between thermal effects and near wellbore effects, far field effects and near wellbore effects? Well, the first time that we treated the open hole zone, we measured low pressures, and when we first did those treatments, and I'll just show the slide. When we first did those treatments, we pumped small volumes, half a barrel a minute, quarter barrel a minute, a barrel a minute, and shut in briefly, very short episodes. And indeed, we did see rollover, we did see closure. But I think the closure was closure of thermally induced fractures due to cool down from the wellbore. And probably these are not a true representation of the in situ stress, that they're probably a function of a fracture that has been of a system that's been cooled down by fluid flowing in the wellbore and cooling the system down. Once we start to pump more fluid in there and we start to process the data, we see higher injection pressures. And so there is a real conundrum here. And we tend to be picking the higher closure stresses rather than the lower closure stresses that we saw with the early low volume injections, because we think that those are associated with cool down.
And other question from Mark Schuster. I assume the natural pre-existing fractures have been characterized from the FMI through the basement. Are you concerned about the interaction with natural fractures inferring with the induced cracks?
Well, that question is more complicated than it sounds. I'm not trying to apologize, but the question is, what are the induced fractures? You probably have relatively short, relatively insignificant induced fractures in this granite. And those induced fractures very soon interact with the natural fracture system. And so possibly the propagation of whatever hydraulic stimulation you're dealing with here is dominantly governed by the natural fracture systems. So the complication there is that there's not one single natural fracture system, and the question is relevant because will these natural fracture systems lead to interaction between supplementary stages of hydraulic fracturing? And the question is, it's very possible that will happen, and we don't know the answer to that yet. And this is sort of one of the things that needs to be determined. Now, if that's the case, then you have to ask yourself, well, what can I do about this? Well, I mean, there's a couple of things you can probably do about this or that can be attempted. And one is, as was pointed out, try pumping proppant. Because if we're going to pump proppant, we're going to likely be using a more viscosified fluid. We're going to have a huge cool down pad to cool down the formation so that the fluid doesn't break. But a viscosified fluid, and the viscous fluid may have less tendency to move into natural fractures intersecting a natural fracture system, that unfavorably oriented natural fractures that are branching off from more favorably oriented natural fractures that are propagating subvertically. So once again, this is absolutely a critical question, and once again, this is yet to be seen from what we have here, and there's a lot of modeling, and the modeling we can make it go either way, and just depending on what specific fracture properties we put in and what sort of treatments we follow. And so this is, once again, this is sort of a stay tuned item that we don't necessarily know what's going to happen at the present time.
So John, thank you very much for addressing the question. There are other questions in the chat, but we have to end the session due to the time constraint. So thank you again for your interesting talk today and for your time. And thank you everyone for your attendance and for your great questions. Hope to see you next week at 9 a.m. Have a wonderful weekend. Thank you.
Thanks, everyone.